construction of alpha from AB into Rn plus 1. Since S is compact, we can say that the compact set S is bounded, and hence there exists a sphere S1 sufficiently large such that S is contained in the interior of S1. Consider the n surface S, and it is possible to find a n sphere S1 such that n surface S is contained in the interior of S1. Now consider the straight line P plus TV belongs to R, where P plus TV where T belongs to R, and this is a straight line which passes through the point P in the direction of V. And here we can see that along when we move along this straight line touches at the sphere at a particular point. That is, there exists a A1 greater than 0 such that P plus A1V belongs to S1. Now define alpha 1 from 0 A1 to Rn plus 1 by alpha 1 of T is equal to P plus TV. Next, consider Q minus TV where T belongs to R, which is also a straight line. This straight line which passes through the point Q in the opposite direction of V. Opposite direction of V. Then as we said in the case of alpha 1, we can find a point A2, that is, there exists a point A2 greater than 0 such that Q plus A2 minus V belongs to S1. Q plus A2 into minus V belongs to S1. Now define alpha 2 from 0 A2 to Rn plus 1 by alpha 2 of T is equal to Q minus TV. Now here when we look at this point P plus A1V and Q minus A2V, these 2 points belongs to S1 and S1 is connected. Hence there exists a continuous map alpha 2 from closed interval B1, B2 to S1 such that alpha 2 of B1 is equal to P plus A1V and alpha 2 of B2 is equal to Q minus A2V. Now take A is equal to 0 and B is equal to A1 plus B2 minus B1 plus A2. Now we are going to define a continuous map on the closed interval AB. Here we have 3 curves and we will construct our required function alpha from closed interval AB into Rn plus 1 by joining these 3 curves. Consider the curve alpha 1 which is in the direction of V and join this curve with the curve alpha 3. Here alpha 2 is the curve in the opposite direction of V. Consider the reverse of this curve which is in this direction and join this curve with alpha 3. By joining these 3 curves, we will get a new curve from a closed interval in R into Rn plus 1. And then we will prove that this curve satisfies all the conditions of alpha. Hence we say this curve is a required curve alpha. Here we can identify the interval closed interval CD by the closed interval AB by using the map which maps T to the point C plus T minus C by B minus A into t minus a. This maps is a 1 on to continuous map from the closed interval AB into CD. By using this map, we reparameterize. That's here we change the domain of. Here we define the curves alpha 3 on the interval A1, closed interval A1 plus B2 minus B1, and change the domain of alpha 2 to the closed interval A1 plus B2 minus B1, A1 plus A2 plus B2 minus B1. Consider the map 5, which assigns t to the point B1 plus B2 minus B1 by A1 plus B2 minus B1 minus A1 into t minus A1, which is equal to B1 plus t minus A1, and it is equal to t plus B1 minus A1. Then the composition of alpha 3 and 5 will be a map from the closed interval A1 plus B2 minus B1 onto the curve alpha 3. Here it is alpha 3. Then the composition of alpha 3 and the map 5 will be a map from closed interval A1 plus B2 minus B1 onto the curve alpha 3. Here alpha 1 will maps the closed interval 0 A1 onto the curve of alpha 1. And next alpha 3 of t plus B1 minus A1 maps the closed interval A1 plus B2 minus B1 onto the curve of alpha 3. The map alpha 2 of A1 plus A2 plus B2 minus B1 minus t is a map from the closed interval A1 plus B2 minus B1, A1 plus A2 plus B2 minus B1 into the curve reverse of the curve alpha 2. Now define the function alpha by alpha of t is equal to alpha 1 of t for 0 less than or equal to t less than or equal to A1, and alpha of t is equal to alpha 3 of t plus B1 minus A1 for A1 less than or equal to t less than or equal to A1 plus B2 minus B1, and it is equal to alpha 2 of A1 plus A2 plus B2 minus B1 minus t for A1 plus B2 minus B1, which is less than or equal to t less than or equal to A1 plus A2 plus B2 minus B1. Now we need to show that alpha will satisfy these conditions. That is, alpha is a continuous function from closed interval AB into Rn plus 1 and differentiable at A and B such that alpha of A equal to P, alpha of B equal to Q, and alpha dot of A equal to PV, alpha dot of B equal to QV, and alpha of T does not belongs to S for A less than T less than B. For that, consider alpha of A. Before that, it is clear we now alpha 1, alpha 2, alpha 3 are continuous functions, and by looking at the definition of alpha, we can say that alpha is a continuous function from closed interval AB into Rn plus 1, where A is equal to 0 and B is equal to A1 plus A2 plus B2 minus B1. Now consider alpha of A, which is equal to alpha 1 of 0, and it is equal to P. So alpha of A is equal to P. Next consider alpha of B, which is equal to alpha of A1 plus B2 minus B1 plus A2, And at last interval, we know that alpha is equal to alpha 2 of alpha of t is equal to alpha 2 of a1 plus a2 plus b2 minus b1 minus t. So here it is equal to alpha 2 of a1 plus b2 minus b1 plus a2 minus a1 plus b2 minus b1 plus a2, and it is equal to alpha 2 of 0. It is equal to q. So this alpha for this function alpha of a is equal to p and alpha of b is equal to q. Now consider the derivative, the velocity of alpha at the point a. That is alpha dot of a, which is equal to alpha dot of 0, and alpha dot of 0 is equal to alpha 1 dot of 0. Now consider alpha 1 of t, then the derivative of alpha 1 of t with respect to t is equal to v, which is a constant, and alpha 1 dash of 0 is also equal to v. So here alpha 1 dot of 0 is equal to the vector alpha 1 of 0, alpha 1 dash of 0, and here alpha 1 of 0 is equal to p and alpha 1 dash of 0 is equal to v. Hence alpha dot of a is equal to p v, and alpha dot of b is equal to alpha of b alpha dash of b. To find alpha dash of b, consider alpha dash of t for t belongs to the last interval a1 plus b2 minus b1, a1 plus a2 plus b2 minus b1. In that interval, alpha of t is equal to alpha 3 of a1 plus b2 minus b1 plus a2 minus t. So the derivative alpha dash of t is equal to alpha 3 dash of a1 plus b2 minus b1 plus a2 minus t into the derivative of a1 plus b2 minus b1 plus a2 minus t. We know the derivative of a1 plus b2 minus b1 plus a2 minus t is equal to minus 1. So alpha dash of t is equal to alpha 3 dash of a1 plus b2 minus b1 plus a2 minus t into minus 1. So alpha dash of b is equal to alpha 3 dash of 0 into minus 1, and we know alpha 3 of t is equal to q minus t v. So the derivative of alpha 3 will be equal to minus v. Hence alpha dash of b is equal to minus v into minus 1, which is equal to v. So alpha dash of b is equal to q v. Now we need to check the second condition, that is alpha of t does not belongs to S for all a less than t less than b. For that, first alpha 1 of t does not belongs to S for all 0 less than t less than or equal to a1. Consider the map G composition alpha from the closed interval 0 a1 into Rn plus 1. Then the derivative of G composition alpha 1 is equal to del G of alpha 1 of t dot alpha 1 dot of t, and it is equal to alpha 1 of t v dot alpha 1 of t v, and it is equal to v dot v, which is equal to norm v equal to 1 strictly greater than 0. Here the derivative of G composition alpha is strictly greater than 0 for all t belongs to the intervals open 0 closed a1. So we can say that therefore G composition alpha is a strictly increasing function on open 0 closed interval a1, that is G strictly increasing along the curve alpha 1, And since g of alpha 1 of 0 is equal to g of p, and it is the maximum value of g on S, we can say that for t such that 0 less than t less than or equal to a1, alpha 1 of t does not belongs to S. Now, second condition, for second curve alpha 2 of t does not belongs to S for all t such that 0 less than t less than or equal to a2. For that, consider the function g composition alpha 2 from closed interval 0 a2 to Rn plus 1, and its derivative is equal to del g of alpha 2 of t dot alpha 2 dot of t, and it is equal to alpha 2 of t v dot alpha 2 of t minus v, and it is equal to v dot minus v, which is equal to minus norm v equal to minus 1, which is strictly less than 0. So g is strictly decreasing along alpha 2. And since g of alpha 2 of 0 is equal to g of q, and it is the minimum value of g on S, and since it is the minimum value of g on S, we can say that for t such that 0 less than t less than or equal to a2, alpha 2 of t does not belongs to S. And for the third curve alpha 2, since alpha 3, since alpha 3 of t belongs to S1, and S is the and the end surface S lies at the interior of S1, we must have alpha 2 of t does not belongs to S for all t belongs to B1, closed interval B1, B2. Since these three curves does not lies in S, we can say that the curve alpha is not belongs to S for t belongs to the open interval AB, and this function alpha is a required map. So we proved the existence of the continuous function alpha from closed interval AB into Rn plus 1.